The cosmos is preparing a rare spectacle in 2025. A parade of wanderers entering the inner solar system, led by the extraordinary interstellar Comet 3I Atlas. What makes this event so remarkable is that 7 additional comets are seemingly following its path, each with its own trajectory, brightness, and story. This celestial caravan offers astronomers and skywatchers a unique chance to observe a cluster of cometary visitors in succession, revealing insights into their origins, behavior, and the dynamic forces shaping our solar system. These icy travelers are not just fleeting streaks of light. They are time capsules carrying secrets of the early solar system and, in Atlas's case, even distant star systems. At the forefront of this icy procession is 3I Atlas, an interstellar comet whose arrival has captivated astronomers and skywatchers alike. Leading this rare cosmic caravan, it sets the stage for a series of comets entering the inner solar system, and its very presence hints at the diversity of material traveling through our galaxy. Unlike typical comets that orbit the Sun in familiar paths, 3I Atlas comes from beyond our solar system, moving at a speed too great to be bound by the Sun's gravity. Its discovery marks only the 3rd confirmed interstellar object, following Oumuamua and 2E Borisov, making it an exceptionally rare visitor that offers a direct glimpse into the chemistry and structure of another star system. 3I Atlas exhibits a brightening coma and a tail visible to sensitive instruments, suggesting the release of volatile ices and dust as it approaches the Sun. Observations indicate it contains carbon-rich compounds and possibly other exotic materials rarely seen in solar system comets. Because it has never been exposed to repeated solar heating, 3I Atlas is essentially a pristine sample of interstellar matter, preserving the conditions of its home system and offering scientists a unique chance to study materials formed around distant stars. Its significance extends beyond composition. As the leader of this remarkable group of comets, 3I Atlas draws attention to the upcoming celestial parade while reminding us that the solar system is not isolated. It is constantly interacting with the broader galaxy. By following its journey, astronomers can track the dynamics of interstellar visitors and their influence on the solar system, all while preparing to observe the other comets seemingly following in its wake. In many ways, 3I Atlas is both a pioneer and a messenger, a visitor carrying secrets from far beyond our Sun, guiding our gaze toward the remarkable succession of cometary wanderers soon to grace our skies. The arrival of 3I Atlas, an interstellar visitor leading a procession of comets, naturally raises an intriguing question. Why are so many comets appearing in the inner solar system around the same time? While 3I Atlas is a rare interstellar phenomenon, the presence of 7 additional comets following closely behind is not merely a cosmic coincidence. It is the result of gravitational forces, orbital dynamics, and the subtle nudges that govern the movement of icy bodies at the edge of our solar system. Understanding why multiple comets appear in succession requires a deep dive into the mechanics of the solar system, particularly the influences of the giant planets, the Sun, and the vast Oort Cloud that surrounds our planetary neighborhood. The solar system is a gravitationally complex environment where even distant objects are affected by the combined tug of multiple bodies. Comets in the outer solar system, especially those originating from the Oort Cloud, exist in a delicate gravitational balance. The Oort Cloud itself is a spherical shell of icy objects extending from roughly 2,000 to over 100,000 astronomical units from the Sun. For millennia, these comets drift in near complete isolation, but their paths are highly susceptible to perturbations. Small changes in trajectory caused by gravitational nudges from passing stars, interstellar objects, or even the collective gravitational influence of the Milky Way. When a sufficiently strong perturbation occurs, an Oort cloud comet can be dislodged from its distant orbit, sent hurtling toward the inner solar system in what astronomers call a long-period orbit, which might take thousands or even millions of years to complete. But the story does not stop there. Once a comet is nudged toward the inner solar system, its journey can intersect with other gravitational influences, especially from the giant planets, Jupiter, Saturn, Uranus, and Neptune. These planetary giants act as cosmic shepherds. Their immense gravitational fields can accelerate comets, redirect their paths, or even break apart weaker bodies, creating clusters of debris or new cometary fragments. This interplay between the initial outer solar system perturbation and the subsequent planetary influences is one reason why multiple comets might appear in the inner solar system around the same time. A single nudge can set off a cascading effect, sending not just one, but several icy bodies along similar trajectories. In essence, the solar system can act like a gravitational conveyor belt, delivering cometary visitors in waves that may appear, to the human observer, almost choreographed. Another factor contributing to the apparent surge of cometary activity is the phenomenon of orbital resonance. When two or more bodies in the solar system have orbital periods that are simple ratios of each other, their repeated gravitational interactions can amplify small orbital changes over time. For comets in the distant reaches of the solar system, resonances with giant planets can subtly align their paths, synchronizing their arrival times in the inner solar system. This means that a comet that was nudged thousands of years ago might be arriving in concert with other long-period comets whose orbits were similarly influenced by these resonances, producing a series of arrivals within just a few years. In 2025, this alignment of cosmic factors has contributed to what could be considered a cometary boom, a rare window during which both interstellar and Oort cloud visitors appear almost simultaneously. It's also worth noting that the increasing number of comet discoveries in recent years is partly due to advances in observational technology. Automated surveys such as ATLAS, Asteroid Terrestrial Impact Last Alert System, SWAN, and MAPS have dramatically increased our ability to detect faint objects at great distances, well before they reach their brightest points near perihelion. While the actual number of comets entering the inner solar system may not have changed significantly, our capacity to detect them early has created the impression of a sudden surge. When coupled with the natural gravitational nudges and alignments that bring comets inward, the observational capabilities of modern astronomy have made it possible to track multiple comets as they follow a similar trajectory, giving us the rare spectacle of an almost simultaneous arrival of several icy bodies. One cannot ignore the possibility that some of these comets are fragments from the same parent body. Cometary fragmentation is a common occurrence, especially for long-period comets venturing close to the Sun for the first time. As the intense solar heating begins to sublimate volatile ices, the structural integrity of the nucleus can fail, creating multiple smaller comets that continue on similar paths. In some cases, these fragments are discovered as separate comets with their own designations, giving the impression of a train of comets. While it is not yet clear whether any of the 2025 comet group is directly related through fragmentation, the phenomenon remains a key factor in explaining clusters of cometary arrivals. In addition, external influences beyond the solar system can play a subtle but important role. Passing stars, molecular clouds, and even the gravitational tides of the Milky Way can perturb the orbits of distant Oort cloud objects. These galactic-scale interactions occur over millions of years, but can have the cumulative effect of sending multiple comets inward along roughly similar directions. The fact that 3I Atlas, an interstellar visitor, is leading a procession of comets may be a visual coincidence, but it also underscores the dynamic environment at the edge of our solar system, where interstellar and solar system influences intersect to create periods of heightened cometary activity. The timing of this cometary wave is also significant because it occurs during a particularly favorable observational window. Earth's position relative to the Sun and the orbital planes of these comets allows astronomers and skywatchers to track their movements with minimal interference from solar glare. Some of these comets, like C 2025 R2 Swan and C 2025 A6 Lemmon, may become visible with binoculars or even to the naked eye if their activity levels increase as expected. This clustering of comets provides an unprecedented opportunity, not only for visual spectacle, but for comparative study. Scientists can examine differences and similarities in composition, activity, and tail morphology among comets that arrive almost simultaneously. Such observations are invaluable for understanding both the diversity of cometary bodies and the processes that govern their journeys. Ultimately, the convergence of multiple comets into the inner solar system at the same time is the result of an intricate cosmic dance. Gravitational nudges from giant planets, perturbations from distant stars, orbital resonances, potential fragmentation, and advances in detection technology all play a role. The result is a rare and compelling display, a natural parade of icy travelers that allows humanity to witness the workings of our solar system and the broader galaxy in real time. It is a vivid reminder that the solar system is not a static collection of planets and asteroids, but a dynamic environment where celestial bodies, from the smallest cometary fragment to interstellar visitors like 3I Atlas, are constantly moving, interacting, and occasionally lining up in ways that capture our imagination. As 2025 continues, astronomers will monitor this procession closely, tracking their brightness, composition, and orbital behavior. Each new discovery adds to the story of how comets travel, fragment, and evolve, offering insight into both the history of our solar system and the conditions in distant star systems. The appearance of multiple comets in a short span of time is more than just a visual phenomenon. It is a living laboratory in the sky, a rare cosmic opportunity that combines spectacle, science, and a reminder of the dynamic, ever-changing nature of the universe. C 2025 R2 Swan is one of the most exciting additions to this cosmic caravan, a comet that has already begun to attract global attention due to its sudden surge in brightness and the tantalizing possibility that it may become a naked eye object in the skies of October 2025. Discovered by the solar wind. Anisotropi's Swan instrument aboard the SOHO spacecraft, which monitors ultraviolet emissions from hydrogen in space. This comet was first identified as a faint object, but quickly revealed itself to be far more dynamic. In the weeks following its discovery, it underwent rapid brightening, a behavior that immediately suggested it might be far more active than astronomers initially expected. For skywatchers, this comet offers the thrilling chance of witnessing one of those rare events when a faint smudge on astronomical charts transforms into a visible streak in the night sky. This comet's early activity hints at a nucleus rich in volatile ices, materials that sublimate rapidly as the comet approaches the warmth of the Sun. Such volatile-driven outbursts are what fuel a comet's coma and tail, and in this case, the rate of activity suggests that the comet may continue to brighten as it draws closer to perihelion. Mid-October 2025 is expected to be its most favorable window for observation, when it could reach brightness levels sufficient to be visible without optical aid under dark skies. While predictions about comet brightness are notoriously uncertain, the rapid increase in luminosity makes this one of the most promising candidates of the year for casual stargazers and dedicated astronomers alike. The discovery of this comet also underscores the power of instruments like SWAN, which specialize in detecting hydrogen emissions. Comets release hydrogen as water ice sublimates into vapor and is broken apart by solar radiation. By detecting these emissions, Swan effectively reveals comets long before they become bright enough for ground-based observers. This is a crucial advantage, as it gives astronomers time to calculate orbits, predict brightness trends, and prepare observation campaigns. The early detection of this comet, followed by its dramatic brightening, has ensured that it will be a major focus of comet watchers in 2025. For scientists, this comet presents more than just a visual treat. Its early activity provides an opportunity to study the mechanisms behind cometary outbursts, the release of dust and gas, and the evolution of its tail structures as solar wind and radiation pressure act upon them. Comparing this comet with others arriving in the same period will allow astronomers to evaluate differences in composition and behavior among comets from different regions of the solar system. This is particularly significant given that it is part of a larger group arriving in quick succession, an ideal natural laboratory for comparative study. As mid-October approaches, anticipation is building. Will this comet flare into a spectacular naked-eye object that dazzles casual skywatchers? Or will it remain a binocular target reserved for dedicated observers under dark skies? The uncertainty is part of what makes comet watching so compelling. Unlike predictable eclipses or planetary alignments, comets carry an element of surprise. Some fizzle out and disappoint, while others erupt into brilliance, becoming unforgettable celestial spectacles. With its rapid brightening and favorable timing, this comet has all the ingredients to become one of the most memorable sights of the year. In the grander scheme of the 2025 comet boom, this comet serves as one of the leading highlights, a potential showpiece in the sky that could captivate millions and spark curiosity about the broader cosmic caravan it belongs to. Whether it shines as a faint streak or a blazing trail, it will add to the story of a rare year when our skies became a stage for multiple icy wanderers journeying inward. One of the most fascinating aspects of Swan is the unpredictable nature of its outbursts. Unlike planets that follow highly predictable orbits or stars that shine with relatively steady light, comets like Swan are dynamic, fragile objects whose behavior can change suddenly and dramatically. Astronomers have already noted that Swan brightened much faster than anticipated shortly after its discovery, a sign that its nucleus is volatile rich and prone to sudden flaring. Such outbursts occur when subsurface ices are rapidly exposed to solar heating, releasing jets of gas and dust that expand outward into the coma and tail. For observers on Earth, these flares can make the comet appear several magnitudes brighter in just a matter of days, transforming a faint telescopic object into a spectacle visible with binoculars, or in rare cases, even to the naked eye. The mystery behind Swan's outbursts lies in the fragile and uneven structure of its nucleus. Cometary nuclei are often likened to dirty snowballs, but in reality, they are far more complex, porous, loosely bound aggregates of dust, rock, and volatile ices such as water, carbon dioxide, carbon monoxide, and methane. When these volatile materials are buried beneath layers of dust or rock, they can remain dormant until the comet approaches the Sun closely enough to heat them. At that point, localized pressure can build up under the surface until it bursts through, causing an explosive release of gas and dust. The result is an outburst that temporarily increases the comet's brightness. In the case of Swan, the rapid brightening observed so far suggests that its nucleus may contain multiple volatile-rich pockets waiting to erupt, making it a prime candidate for repeated flaring episodes as it journeys inward. For scientists, these outbursts present both challenges and opportunities. On the one hand, they make predicting the comet's brightness notoriously difficult. A sudden outburst can elevate Swan to naked-eye visibility, drawing global attention. But if the flares are weak or inconsistent, the comet might remain accessible only through binoculars or telescopes. On the other hand, these unpredictable eruptions are windows into the internal structure and composition of the nucleus. By observing the timing, frequency, and composition of outbursts, astronomers can infer details about the layering of materials inside the comet, the size and distribution of volatile deposits, and the processes that govern their release. Each flare becomes not just a visual phenomenon, but a scientific clue, a rare chance to peer beneath the surface of a comet that has likely remained unchanged for millions of years. The unpredictability of Swan's outbursts also captures the imagination of skywatchers. Unlike well-timed eclipses or planetary alignments, comets carry a sense of mystery and anticipation. No one can say for certain how bright Swan will become or how long it will remain visible. This uncertainty fuels excitement, as observers worldwide prepare for the possibility of a sudden cosmic show. Amateur astronomers play a vital role in this process, as they can monitor the comet continuously and report flares almost in real time, often spotting brightening events before professional observatories can respond. This collaborative effort between professional and amateur communities adds a unique human dimension to the study of Swan, uniting science and wonder under the night sky. Another factor that makes Swan's potential outbursts so intriguing is their timing. The comet's closest approach and perihelion passage in mid-October 2025 align with a period when it will be favorably placed in the sky for many observers on Earth. If an outburst occurs during this window, Swan could become one of the most striking celestial events of the decade, rivaling the great comets of the past. Even a modest flare could make it visible from dark sky locations without optical aid, while a significant outburst might render it a spectacular object easily seen from suburban skies. In a time when light pollution limits our view of the cosmos, the possibility of Swan suddenly bursting into brilliance offers a rare chance for millions of people to reconnect with the raw, unpredictable beauty of the universe. There is also the possibility that Swan's outbursts could be precursors to larger structural changes. Comets that flare dramatically are often unstable, and in some cases, repeated outbursts foreshadow fragmentation or disintegration. If Swan's nucleus is particularly fragile, the stresses of solar heating and rotational forces could eventually cause it to split into multiple fragments. Such an event would not only provide a dazzling display, but also deliver invaluable data about the internal composition of the comet. Fragmentation events have been observed before. For example, Comet 73P Schwarzmann-Wachmann 3, which broke into dozens of pieces in 1995. Should Swan undergo a similar fate, astronomers would be able to study the freshly exposed interiors of the fragments, offering a rare opportunity to directly analyze pristine cometary material. The scientific importance of monitoring Swan's unpredictable behavior cannot be overstated. Each outburst, whether minor or dramatic, adds a piece to the puzzle of cometary physics. By comparing Swan's activity to that of other comets arriving in the same period, such as Lemmon, Atlas, and Vosh, researchers can identify similarities and differences that reveal how comets from different origins respond to solar heating. These insights deepen our understanding of cometary diversity and shed light on the processes that shaped our solar system billions of years ago. In particular, studying how Swan responds to solar energy may help refine models of how volatile rich bodies delivered water and organic compounds to early Earth, potentially influencing the origins of life itself. For the public, however, Swan's greatest contribution may be its unpredictability. The possibility that it could flare into naked-eye visibility creates a sense of anticipation that few other celestial events can match. It is this blend of uncertainty and spectacle that has made comets objects of fascination for centuries, inspiring awe, myth, and wonder around the world. Whether Swan becomes a faint smudge in the telescope or a dazzling streak across the night sky, its outbursts remind us that the universe is alive, dynamic, and often full of surprises. C2025A6 Lemmon is another remarkable participant in the ongoing cometary procession, arriving in tandem with Swan and adding to the sense that the skies of 2025 will be unusually lively. While Swan has already shown itself to be unpredictable with its sudden outbursts, Lemmon has been building steady anticipation of its own. First identified by the Mount Lemmon survey in early 2025, this comet quickly drew attention for its favorable orbit and its potential to become bright enough for widespread observation. With its perihelion occurring in October 2025, close to the same time frame as Swan's best visibility, Lemmon stands out as a second act in this unfolding cosmic performance, providing both scientists and stargazers with another icy traveler to watch. The potential of Lemmon lies in its predicted brightness. Early estimates suggest that it may reach magnitudes accessible through binoculars, and under the right conditions, it could even become visible to the naked eye. While comets are notoriously difficult to predict, some remain faint despite initial optimism, while others unexpectedly flare into brilliance. Lemmon's trajectory and activity levels so far have kept hopes alive for a striking apparition. For those who follow celestial events, the possibility of observing two bright comets in a single season is rare, and Lemmon's timing alongside Swan makes 2025 an especially memorable year for comet enthusiasts. The two together create a sense of a cosmic duet, complementing each other in brightness and visibility, and offering skywatchers multiple opportunities to catch sight of these icy visitors. From a scientific perspective, Lemmon carries significant importance as well. Unlike 3I Atlas, which hails from interstellar space, Lemmon is a product of our solar system, likely originating from the Oort Cloud, the vast reservoir of icy bodies at the edge of the Sun's gravitational reach. Studying Lemmon provides astronomers with a valuable point of comparison. By contrasting the composition and activity of Lemmon with those of Swan and 3I Atlas, researchers can deepen their understanding of how cometary bodies from different origins behave as they approach the Sun. This kind of comparative study is at the heart of modern cometary science, helping refine theories of solar system evolution and the delivery of volatile materials to planetary surfaces. Lemmon also carries with it a legacy. The name Lemmon has appeared multiple times in cometary history, with previous discoveries by the Mount Lemmon survey producing bright comets that delighted observers and challenged scientific assumptions. For many astronomers, the reappearance of the Lemmon name sparks a sense of continuity and excitement, reminding us of how each new comet discovery builds on a rich tradition of skywatching. The reputation of the survey itself has only grown over the years, becoming one of the leading programs for detecting near-Earth objects and comets alike. In this sense, C2025A6 Lemmon is not just another icy traveler. It is part of a broader legacy of exploration and discovery, a symbol of humanity's persistent curiosity about the dynamic skies above. For observers on Earth, Lemmon promises to be relatively accessible, with a favorable viewing window coinciding with dark autumn skies in the Northern Hemisphere. If predictions hold, binoculars may be enough to reveal its glowing coma, and perhaps even a faint tail stretching away from the Sun. Should Lemmon experience any outbursts, similar to those Swan has already shown, it could briefly become one of the brightest comets in years, a spectacle visible even from light-polluted areas. Such an event would not only provide a stunning view, but also offer scientists rare data about the behavior of Oort Cloud comets on their first or second approaches to the Sun. As October 2025 approaches, the sense of anticipation grows. With Swan already making headlines for its unpredictability, Lemmon is poised to add depth to the narrative, enriching this celestial parade with its steady glow. Together, they embody the diversity of comets: Swan, volatile and unpredictable, bursting with outbursts, and Lemmon, steady and promising, rooted in a legacy of discoveries. Their nearly simultaneous arrivals remind us that the cosmos often delivers its wonders in clusters, offering not just a fleeting event, but an extended season of discovery and awe. The excitement surrounding C 2025A6, Lemmon, is amplified by the rich history associated with the Lemmon name in cometary science. The Mount Lemmon survey, located in Arizona, has been a prolific source of comet discoveries for decades, contributing not only to our catalogue of near-Earth objects, but also to our understanding of the diverse population of comets within the solar system. Over the years, comets bearing the Lemmon designation have produced several notable apparitions that captured both the attention of astronomers and the imagination of the general public. These previous discoveries were often characterized by unexpected brightness, long tails, or peculiar behaviors that challenged existing models of cometary physics. And in this context, the arrival of another Lemmon comet carries with it a sense of anticipation grounded in historical precedent. The legacy of Lemmon comets extends beyond mere observation. It is intertwined with the advancement of cometary science. Each discovery made by the Mount Lemmon survey has offered astronomers a unique opportunity to study the composition, activity, and evolution of icy bodies from different regions of the solar system. For example, earlier Lemmon comets have been observed displaying sudden outbursts, fragmenting into multiple pieces, or producing unusually bright dust tails. Phenomena that provide critical data about the structural integrity, volatile content, and sublimation processes of cometary nuclei. In the case of C 2025A6, astronomers are particularly eager to monitor these parameters, as doing so will allow comparisons with both the other comets arriving in 2025, like Swan and 3I Atlas, and with historical Lemmon discoveries. By situating this comet within the broader narrative of Lemmon comets, scientists can identify patterns in behavior, detect subtle variations in chemical composition, and refine models that explain why certain comets brighten dramatically while others remain faint. One of the reasons the Lemmon survey has been so successful is its technological edge. Equipped with high-sensitivity CCD cameras and wide-field telescopes, the observatory can detect faint objects at great distances, sometimes long before they reach their brightest phases. This early detection capability is particularly important when tracking comets that may exhibit unpredictable behavior, like C 2025A6. Early observations allow astronomers to calculate precise orbital elements, forecast perihelion passages, and prepare coordinated observation campaigns that include professional observatories and dedicated amateur astronomers. In essence, the legacy of Lemmon comets is not just a series of bright spectacles, it is a testament to the marriage of technological innovation and scientific curiosity, a combination that has expanded our understanding of cometary populations and the dynamical forces shaping their journeys. Historical Lemmon comets have also played a role in public engagement with astronomy. Comets like C 2012 K1, Lemmon, and C 2013 V5, Ukaimeden Lemmon, captured widespread attention, providing dramatic visuals and sparking curiosity about the nature of these icy travelers. They reminded the public that the solar system is not a static environment. It is dynamic, with objects constantly moving, interacting, and occasionally offering spectacular shows for those who look up. This cultural and educational impact is an often overlooked aspect of the Lemmon legacy. Each new comet becomes an opportunity to connect people with the broader cosmos, inspiring wonder, curiosity, and sometimes even prompting amateur astronomers to contribute valuable observations to the scientific record. The arrival of C 2025A6 thus carries not only scientific significance, but also a potential for public engagement, echoing the excitement of past Lemmon comets and reminding us that celestial events have the power to unite curiosity and spectacle in a single, shared experience. In addition, the consistency of Lemmon comet discoveries has given astronomers a valuable comparative framework. By studying multiple Lemmon comets over time, researchers have been able to track variations in activity, tail morphology, and chemical composition across different objects originating from potentially similar regions of the Oort Cloud. These comparisons have revealed subtle but significant differences that inform our understanding of cometary formation and evolution, suggesting that even comets sharing similar orbits or discovery conditions can have widely varying physical characteristics. C 2025. A6 provides another opportunity to expand this dataset, adding fresh information that may confirm previous patterns or reveal unexpected anomalies. For example, monitoring whether Lemmon follows a predictable brightening curve or exhibits unusual outbursts like Swan could shed light on the structural diversity of cometary nuclei and the factors that influence their activity. Furthermore, the legacy of Lemmon comets underscores the importance of observational persistence. Many significant cometary discoveries require repeated monitoring over weeks or months, particularly when the objects are faint or distant at first. The Mount Lemmon survey has consistently demonstrated the value of such persistence, often catching comets early enough to allow extensive study of their development and behavior as they approach perihelion. In this sense, C 2025A6 is the latest chapter in an ongoing story. It is a comet that arrived on the radar of astronomers due to diligent observation, and it now has the potential to add new insights into both the mechanics and chemistry of these icy wanderers. The excitement surrounding Lemmon is further amplified by its timing within the 2025 to 2026 cometary window. Following closely after Swan and ahead of other notable discoveries like C 2025K1, Atlas, and C 2025Q1, Atlas, Lemmon is positioned as a bridge between interstellar and solar system cometary visitors. Its predictable trajectory and comparatively steady brightness offer a counterpoint to the unpredictability of Swan, allowing astronomers to compare behaviors under similar solar conditions. This juxtaposition enhances the scientific value of observing multiple comets in succession. By studying Lemmon alongside its fellow travelers, researchers can investigate how origin, composition, and past solar exposure influence activity levels, tail formation, and overall brightness. In other words, the legacy of Lemmon comets not only inspires anticipation for visual spectacle, but also provides a vital reference point for scientific investigation, helping contextualize the behavior of newer and more exotic comets like 3I Atlas. C 2025 K1 Atlas is the next fascinating traveler in the 2025 celestial procession, discovered by the Atlas survey, which has become renowned for its prolific identification of comets and near-Earth objects. This comet has attracted attention not only for being a recent addition to our catalogue of icy wanderers, but also for its trajectory, which brings it into the inner solar system near the end of 2025, coinciding with Earth's favourable viewing position. Unlike Swan, which is already showing unpredictable flaring, and Lemmon, which has a more gradual brightening, this comet presents astronomers with an opportunity to track a relatively young discovery as it approaches perihelion, offering fresh insights into the behaviour of newly observed comets. The significance of this comet lies in both its timing and its discovery source. Atlas, the survey responsible for spotting it, has a well-established track record of identifying comets that later become major observational targets. The survey's automated telescopes, designed to detect transient objects, scan vast areas of the sky each night, enabling the early detection of objects that might otherwise have gone unnoticed until much closer to Earth. In the case of this comet, early detection allows astronomers to calculate its orbit with precision, predict its closest approaches to the Sun and Earth, and prepare for detailed observational campaigns. The late 2025 perihelion promises to be the most favourable period for observation, as the comet will be near its brightest and positioned high enough in the sky for optimal visibility. Preliminary observations suggest that this comet has a moderately active nucleus, with a coma developing steadily as it nears the Sun. While it has not yet exhibited dramatic outbursts like Swan, its gradual increase in brightness indicates the presence of volatile ices that will sublimate as solar radiation intensifies. Astronomers are particularly interested in monitoring this comet's activity in the months leading up to perihelion to determine whether it follows a predictable pattern of brightening or whether unexpected flares might occur. These observations will provide valuable comparative data, especially when analysed alongside the other comets arriving in the same period. Understanding variations in activity levels, dust production, and tail formation among comets discovered by different surveys helps refine models of cometary physics and the diverse nature of these icy bodies. The trajectory of this comet also presents a promising observational opportunity for both amateur and professional astronomers. Its perihelion, scheduled for late 2025, will coincide with a period when Earth-based observers can track it for extended periods during the night, minimizing interference from the Sun and maximizing the chances of capturing detailed images and spectra. Depending on its final brightness, this comet could be a binocular target for amateur observers and, in the event of an outburst, potentially visible to the naked eye under dark sky conditions. For professional astronomers, the comet offers the chance to study the composition of its coma and tail, including measurements of gas species, dust grain sizes, and the dynamics of dust jets, providing a snapshot of material that has likely remained largely unchanged since the formation of the solar system. The discovery of this comet by the Atlas survey underscores the importance of modern sky surveys in the ongoing study of comets. Atlas has rapidly become a powerhouse in comet detection, responsible for identifying some of the most notable cometary visitors of recent years. By scanning the skies nightly with automated telescopes and sophisticated software, Atlas can detect faint, fast-moving objects that may otherwise elude traditional observation methods. Each new discovery, including this comet, adds to our understanding of the population of comets in the solar system, the distribution of their orbits, and the mechanisms that bring them into the inner regions where they become observable. The comet is, in a sense, part of a broader narrative, a product of both natural cosmic processes and human ingenuity in detection and tracking. Another aspect that makes this comet particularly interesting is its potential for coordinated, multi-wavelength observations. As it approaches perihelion, astronomers will likely monitor it across the electromagnetic spectrum, from visible light to infrared and even radio wavelengths, to study the composition and behavior of its coma. Observations of this comet in the ultraviolet and infrared bands can reveal the presence of water vapor, carbon dioxide, and other volatiles, while radio measurements can help detect molecules like hydrogen cyanide or carbon monoxide. These multifaceted observations provide a more complete picture of the comet's composition and activity, offering insights into the chemical diversity of cometary bodies and how they may relate to the conditions present during the early formation of the solar system. Additionally, this comet serves as a link between the highly unpredictable behavior of Swan and the steady performance of Lemmon, allowing astronomers to study the continuum of cometary activity within a single observational season. By examining comets that arrive in quick succession but exhibit different levels of activity and brightness, researchers can begin to identify patterns and anomalies that reveal the influence of factors such as nucleus composition, prior solar exposure, and orbital dynamics. This comparative approach enhances the scientific value of observing multiple comets within the same period, transforming what might otherwise be isolated observations into a cohesive study of the behavior of icy bodies entering the inner solar system. The late 2025 approach of this comet also raises the possibility of public engagement. As with Swan and Lemmon, amateur astronomers equipped with small telescopes or binoculars may be able to track the comet's progress, while photographers can attempt to capture its developing tail and coma. The timing provides a rare opportunity to observe multiple comets within a single season, offering skywatchers a kind of comet festival that reinforces the dynamic and ever-changing nature of our solar system. The anticipation surrounding this comet, together with the simultaneous visibility of other bright comets, ensures that 2025 will be remembered as an extraordinary year for comet observation and study. In many ways, this comet exemplifies the ongoing impact of the Atlas survey on modern cometary astronomy. Its discovery, orbit, and predicted visibility highlight the synergy between automated sky surveys and traditional observational techniques, demonstrating how technology enhances our ability to study these ancient celestial travelers. As it approaches perihelion, astronomers will continue to monitor its brightness, coma development, and tail formation, ensuring that this newly discovered comet adds its story to the rich tapestry of the 2025 Cometary Parade. The discovery of this comet by Atlas naturally leads us to consider the broader impact of the Atlas survey itself, a program that has rapidly become one of the most prolific comet detection engines in modern astronomy. Officially known as the Asteroid Terrestrial Impact Last Alert System, Atlas was originally designed to detect near-Earth objects that could pose a potential hazard, but its high-sensitivity telescopes and wide-field cameras have proven equally adept at identifying distant, fast-moving comets. Over the past decade, Atlas has produced a string of discoveries, from minor icy bodies to major comets that have captured the attention of astronomers and the public alike. Its ability to scan vast regions of the sky every night has revolutionized the way we discover and track cometary objects, making it a cornerstone in contemporary comet science. What makes the Atlas survey particularly powerful is its combination of automation and coverage. Its telescopes, situated in Hawaii, operate with highly sensitive CCD cameras that capture faint light from distant objects, detecting them long before they would be visible with traditional methods. The survey software then analyzes the images, comparing them against known objects to identify new potential discoveries. This combination of technology and strategy allows Atlas to identify comets that might otherwise remain invisible until they approach the inner solar system. It is precisely through this method that comets like C 2025 K1 Atlas and C 2025 Q1 Atlas have been detected early enough to allow months of preparatory observation, orbit calculation, and public awareness campaigns. In this sense, the Atlas survey functions not only as a discovery tool, but also as a bridge between the vast reaches of the solar system and the astronomers who study it. Atlas's contributions extend beyond simply finding new comets. The survey has reshaped our understanding of the population and behavior of these icy wanderers. By cataloguing and monitoring numerous comets over the years, Atlas has provided valuable data about orbital distributions, rates of brightening, and frequency of outbursts. This wealth of information has allowed astronomers to identify patterns in cometary behavior, differentiate between short-period and long-period comets, and even detect rare interstellar visitors like 3I Atlas. In essence, ATLAS has become a critical tool for statistical studies of cometary populations, offering insights into how comets are distributed across the solar system and the factors that influence their paths toward the inner planets. One of the remarkable aspects of the ATLAS survey is its ability to detect comets at different stages of their journey toward the Sun. Some comets are discovered when they are still faint and distant, providing months or even years of lead time for observation. Others appear closer to the inner solar system, often brightening quickly as they approach perihelion. This dual capability has allowed ATLAS to contribute both to long-term scientific planning and to the excitement of real-time observation, where astronomers and amateur observers alike can witness dramatic changes in comet brightness and tail structure. In 2025, the simultaneous presence of multiple ATLAS-discovered comets, including C 2025 K1 and C 2025 Q1, highlights the survey's continued importance in expanding our understanding of the dynamic solar system. ATLAS's impact is not confined to individual discoveries. It also fosters collaboration within the astronomical community. By publicly releasing discovery data promptly, ATLAS enables astronomers worldwide to conduct follow-up observations, collect spectroscopic measurements, and study cometary activity across multiple wavelengths. This collaborative approach ensures that each discovery is maximized for scientific value, creating a networked system of observation that spans continents and utilizes telescopes both large and small. In the case of C 2025 K1, this means that by the time it reaches perihelion, there will be extensive datasets available, including observations of gas production rates, dust tail morphology, and rotational behavior of the nucleus. Such comprehensive studies would be far more difficult without the early detection and open data policies of the ATLAS survey. The influence of ATLAS extends to public engagement as well. Its discoveries frequently capture media attention, sparking curiosity and excitement about the night sky. By finding comets that have the potential to become visible to amateur astronomers, ATLAS bridges the gap between professional science and public experience. People around the world can follow these comets in real time, track their movement, and even photograph their evolving tails. In 2025, as Swan, Lemmon, and multiple ATLAS comets traverse the inner solar system, the combination of unpredictability, legacy, and precise discovery will provide a unique season for both scientific observation and public enjoyment. In addition, ATLAS's efficiency in detecting comets contributes to a broader understanding of how common such arrivals are. By increasing the number of known comets each year, the survey helps refine estimates of the total population of long-period and short-period comets in the solar system. This information is crucial for understanding the structure and dynamics of the Oort Cloud, the Kuiper Belt, and the pathways that lead comets into the inner solar system. It also helps contextualize unusual arrivals, such as 3I Atlas, an interstellar comet, by providing a baseline for what is typical in cometary behavior. The combination of routine discoveries and rare events allows astronomers to paint a more complete picture of the solar system's dynamism. C 2025 Q1 Atlas represents yet another exciting addition to the 2025 Comet catalogue discovered by the ATLAS survey and quickly becoming a subject of interest for astronomers worldwide. This comet, like C 2025 K1, was detected well before reaching its closest approach to the Sun, allowing for detailed orbital calculations and planning of observational campaigns. Its designation, Q1, signifies that it is one of the early discoveries in the second half of 2025, entering the ever-growing catalogue of comets for the year and reinforcing the notion that this is a particularly active period for cometary arrivals. Each new designation carries weight in both scientific and observational communities, as it marks an opportunity to study an icy body that may reveal unique insights into the formation and evolution of the solar system. This comet stands out because it represents the continuing efficiency and precision of the ATLAS survey. By identifying comets early, ATLAS provides astronomers the time to observe their behavior as they approach perihelion, track any changes in brightness, and analyze their chemical composition. Early detection is particularly important for non-periodic comets, which may only visit the inner solar system once. Each such discovery, including this comet, becomes a rare opportunity to gather data that might never be obtainable again. As a result, fresh discoveries like this comet carry immense scientific value, expanding our understanding of cometary diversity and the processes that govern their activity as they interact with the Sun's radiation and the solar wind. Observationally, this comet may also become an accessible target for amateur astronomers and skywatchers, depending on its ultimate brightness and position in the sky. While some newly discovered comets remain faint, requiring powerful telescopes to see, others can brighten unexpectedly, much like Swan did earlier in 2025. Monitoring this comet over the coming months allows scientists to predict whether it will remain a telescopic object or potentially develop into a more visible spectacle, perhaps even for naked eye observers under favorable conditions. Its progression offers a complement to the other comets of the season, providing a broader perspective on the range of brightness and activity levels among recently discovered icy bodies. The importance of this comet extends to comparative studies with other comets in the 2025 cohort. By observing how it behaves relative to K1, Lemmon, and Swan, astronomers can identify similarities and differences that may be influenced by origin, composition, and previous solar exposure. While Swan is interstellar and Lemmon likely hails from the Oort Cloud, this comet provides a data point that may fall somewhere between these extremes, helping refine models of comet formation and evolution. Such comparative analysis is critical in understanding the underlying processes that govern cometary activity, including outbursts, tail formation, and coma development. Each newly observed comet adds a piece to the larger puzzle of how icy bodies evolve and respond to the solar environment. In addition, the discovery of this comet highlights the broader implications of maintaining comprehensive comet catalogues. By continuously adding new objects, surveys like ATLAS allow astronomers to track long-term trends in comet frequency, orbital characteristics, and behavior. This is essential for developing accurate models of the solar system's structure, including the Oort Cloud and the distribution of long-period comets. Each new designation, such as Q1, represents not just a single object, but a part of the statistical framework that helps scientists understand the likelihood of comet arrivals, their typical brightness, and potential hazards to Earth. The catalogue thus serves both scientific and practical purposes, informing research and planetary defense strategies alike. From a historical perspective, fresh discoveries like this comet are also vital because they maintain the continuity of cometary research. Comets observed in the past may have returned or fragmented, but many are only seen once. By discovering new comets each year, astronomers ensure that the study of these icy visitors remains ongoing, with a steady influx of new objects to analyze. This continuity allows for the refinement of observational techniques, the testing of theoretical models, and the comparison of new data with historical records. Each new entry in the Comet catalogue adds to a living archive of solar system knowledge, providing insights that may inform everything from the dynamics of the outer solar system to the origins of water and organic compounds on Earth. The scientific value of observing this comet is further amplified when considered alongside the other members of the 2025 cometary wave. Its arrival, along with Swan, Lemmon, and K1, demonstrates that this period is unusually rich in observable comets, offering a rare chance to study multiple objects under similar solar conditions. Such an opportunity is invaluable. Astronomers can compare activity levels, brightness evolution, and tail morphology across several comets, gaining insights into the influence of solar heating, rotational dynamics, and chemical composition. This comparative approach transforms what might otherwise be isolated observations into a coherent, larger-scale investigation of cometary behavior. As the 2025 Comet Parade continues, attention turns to a newcomer that has recently entered the official discovery lists. C 2025 O2 MAPS. While many of the season's comets have been tracked and anticipated for months, this comet represents a fresh arrival, offering astronomers a unique opportunity to study an object that is still in the early stages of its journey into the inner solar system. Its discovery by the MAPS survey, a relatively smaller but increasingly effective sky scanning program, highlights the expanding network of observatories contributing to our understanding of cometary populations. Each new detection, particularly one as recent as this comet, injects excitement into both scientific and amateur observing communities, emphasizing that the night sky is a dynamic and constantly evolving stage. This comet, being a newcomer, carries the intrigue of unpredictability. Its brightness and activity levels are still being monitored, and astronomers are particularly interested in how it will respond as it approaches the Sun. Unlike Swan, which has already demonstrated dramatic outbursts, or Lemmon, whose brightness is more gradual and steady, this comet presents a blank canvas. Its future behavior is uncertain, making early observations critical for establishing baseline data. The fact that it has entered the official discovery list so recently means that astronomers now have the chance to document its development from an early point, tracking changes in its coma, tail, and potential outbursts as solar heating begins to influence its icy nucleus. The discovery of this comet underscores the growing role of smaller survey programs in complementing the efforts of major observatories like Atlas or Mount Lemmon. MAPS, with its wide-field imaging capabilities, contributes to a more complete picture of cometary populations by identifying objects that may be faint, distant, or previously overlooked. In the case of this comet, early detection allows for prompt orbital calculations and trajectory predictions, giving both professionals and amateurs time to plan observation schedules. The fact that it has been added to the official discovery lists indicates that its orbit has been sufficiently confirmed, but ongoing monitoring will continue to refine our understanding of its path and future visibility. This comet also offers an important comparative perspective. Observing it alongside the other comets active in 2025, such as Swan, Lemmon, and the Atlas discoveries, provides astronomers with an opportunity to study differences in origin, composition, and activity under similar solar conditions. While some comets in this group hail from the distant Oort Cloud and others, like 3I Atlas, are interstellar, this newcomer's origin is likely from the outer reaches of our own solar system. Studying the way its nucleus reacts to solar heating, the rate of gas and dust production, and the development of its tail can reveal subtle variations that improve models of comet formation and evolution. These comparisons are essential for building a comprehensive understanding of the diversity of icy bodies entering the inner solar system. For observers on Earth, this comet offers the promise of a new target to follow over the coming months. Depending on how bright it becomes, binoculars or even small telescopes may reveal its developing coma and tail, while potential outbursts could briefly elevate it into visibility for naked-eye viewers. Its emergence at this stage of the 2025 Comet season enhances the overall experience of skywatchers, providing an additional object to track in a year already rich with cometary activity. Such fresh arrivals serve as reminders that the solar system is far from static, with icy bodies constantly moving along complex orbits, occasionally entering our line of sight and offering moments of cosmic spectacle. The timing of this comet's appearance is particularly interesting. Following the sequence of Swan, Lemmon, and the Atlas discoveries, it reinforces the notion that 2025 is an unusually active period for cometary arrivals. Observing multiple comets in rapid succession allows astronomers to gather comparative data under similar conditions of solar radiation and orbital positioning, enhancing scientific understanding of factors like nucleus activity, tail morphology, and the influence of gravitational interactions with planets. In addition, the sheer number of comets present within the same time frame increases the probability of witnessing rare phenomena such as outbursts, fragmentation events, or unusual tail formations, making this season especially valuable from a research perspective. From a scientific standpoint, this comet highlights the importance of continuous sky surveys and the collaborative nature of modern astronomy. By contributing new discoveries to the global catalogue, the MAP survey helps ensure that no potential cometary visitor goes unnoticed. Early detection enables coordinated observations across multiple wavelengths, including visible, infrared, and radio, which can reveal the chemical composition, dust-to-gas ratios, and other characteristics that provide clues about the comet's origin and history. This comprehensive approach maximizes the knowledge gained from each discovery, ensuring that even newly detected comets like this one can provide meaningful contributions to our understanding of the solar system. The growing number of comet discoveries in 2025 naturally brings us to the topic of how these icy visitors are named. A system that, while structured, can appear complex at first glance. Comet names follow a standardized convention designed by the International Astronomical Union, allowing astronomers to quickly understand the timing, nature, and discoverer of each object. The first part of a comet's designation indicates whether it is periodic or non-periodic. Non-periodic comets, which may pass through the inner solar system only once, receive the prefix C/, while periodic comets that return at regular intervals receive the prefix P/. This initial classification helps distinguish between long-period visitors from the Oort cloud or interstellar space and short-period comets that orbit more frequently within the solar system. Following the prefix, the year of discovery is included, immediately situating the comet within a temporal context. For example, C 2025 Q1 Atlas was discovered in 2025, making it part of that year's comet catalogue. The next portion of the designation consists of a letter and number combination, which provides additional chronological information. The letter corresponds to the half-month period of discovery, with A representing the first half of January, B the second half, and so on. And the number indicates the sequence of discovery within that period. This system ensures that each comet receives a unique identifier, avoiding confusion even when multiple comets are discovered within the same time frame, as is the case in this particularly active season. The final element of a comet's name is typically the surname of the discoverer or the name of the survey responsible for finding it. This is why designations like Atlas, Lemmon, and MAPS appear in parentheses following the formal designation. These names acknowledge the human or institutional contribution to discovery, honoring the individuals and teams whose work makes these observations possible. For instance, Atlas refers to the Asteroid Terrestrial Impact Last Alert System survey, which has discovered multiple comets in recent years, while Lemmon references the Mount Lemmon survey, and MAPS acknowledges the contributions of the Minor Planet and Asteroid Physical Survey. In each case, the name links the comet to its origin of discovery, providing context for future observations and scientific studies. Understanding this naming system also allows astronomers to immediately infer certain properties about a comet. By reading the designation, a researcher can identify whether the comet is likely to return periodically, estimate when it was first observed, and determine which observatory or survey first recorded it. This streamlined approach is essential in a year like 2025, when multiple comets, Swan, Lemmon, the Atlas discoveries, and the Newcomer from MAPS are entering the inner solar system in rapid succession. The standardized names help organize observations, coordinate global study efforts, and ensure that each comet's data is accurately tracked over time. Additionally, the naming system reflects a balance between tradition and modern discovery methods. Historically, comets were often named after their first observed discoverers, usually individuals who happened to notice them with modest telescopes. Today, automated surveys and advanced telescopes dominate the discovery process, but the tradition of honoring the discoverer remains intact, resulting in names like Atlas, Lemmon, and MAPS. This continuity provides a link between centuries of cometary observation and the cutting-edge technologies of the present, highlighting the evolution of observational astronomy while maintaining recognition for human contributions. The clarity provided by this naming convention also supports communication within the scientific community and beyond. When a comet like C 2025-02 MAPS or C 2025-K1 Atlas is discussed in publications, research papers, or news releases, the name immediately conveys its discovery, year, order, and source, reducing ambiguity. Amateur astronomers and skywatchers also benefit from this system, as it allows them to track comets accurately, locate them in the sky, and coordinate observations with professional datasets. In effect, the naming convention functions as both a scientific shorthand and a cultural acknowledgement of discovery, bridging the professional and public aspects of cometary observation. In the context of the 2025 cometary season, this system becomes particularly valuable. With multiple comets approaching the inner solar system in close succession, the standardized names allow astronomers to differentiate between Swan, Lemmon, Atlas comets, and the Newcomer from MAPS without confusion. Each designation serves as a compact summary of critical information, enabling coordinated observation campaigns, timely data collection, and comparative studies across multiple comets. The naming conventions also remind us of the human and technological networks behind these discoveries, illustrating how structured scientific practices intersect with the awe-inspiring spectacle of these icy travelers. Ultimately, the naming system does more than label objects. It tells a story of discovery, timing, and collaboration. It captures both the history of a comet's observation and the legacy of the people or programs responsible for finding it. In the case of the 2025 Cometary Parade, the names Swan, Lemmon, Atlas, and MAPS serve as markers of a vibrant, dynamic season, each pointing to a different origin, discovery method, and journey through the solar system. This system allows astronomers and enthusiasts alike to follow the comet's paths with precision and context, enhancing both the scientific value and the public experience of observing these fleeting, magnificent visitors. As we continue tracking the celestial lineup, attention turns to C 2024 E1 Vosh, an Oort Cloud visitor that promises to join the parade of comets entering the inner solar system over the next year. This comet is particularly intriguing because, unlike the recent arrivals of 2025, it originates from the distant Oort Cloud, a vast reservoir of icy bodies that extends nearly a light year from the Sun. The Oort Cloud is thought to be the source of long-period comets, and each object that ventures inward provides a rare glimpse into the primordial materials that formed the solar system. With perihelion set for January 2026, This comet offers astronomers the opportunity to study one of these deep-time messengers, bridging the gap between our current observations and the ancient history of our planetary neighborhood. This comet's trajectory is significant because it allows for a relatively extended observation window before it reaches its closest approach to the Sun. Early monitoring will enable astronomers to determine its activity levels, measure the development of its coma, and track the formation of any tails composed of gas and dust. Unlike periodic comets, whose repeated passages have altered their surfaces through repeated solar heating, this comet may retain a largely pristine composition, making it especially valuable for studies of primordial ices and organic compounds. Each observation contributes to a larger understanding of the solar system's formation, helping to identify the chemical building blocks that may have been present when the Sun and planets coalesced. The Oort Cloud origin of this comet emphasizes the sheer scale and complexity of our solar system. It illustrates how gravitational interactions, both from passing stars and from the collective influence of the galaxy, can perturb distant icy bodies and send them plunging toward the Sun. Such events are rare on human timescales, and each long-period comet that enters the inner solar system provides an invaluable opportunity to study the dynamical processes that govern these distant reservoirs. Observing this comet as it moves inward allows astronomers to examine how objects with little prior solar exposure respond to increased radiation, how their volatile compounds sublimate, and how their dust and gas tails develop in response to solar wind and pressure. For skywatchers and amateur astronomers, this comet adds another layer of anticipation to the already crowded cometary season. While some of the 2025 comets may have already peaked or are fading, this Oort Cloud visitor will arrive at a time when observational conditions may be favorable, potentially offering a bright display for those tracking its progress. Its appearance reinforces the concept of a cosmic train, where comets arrive in succession, each adding its unique character to the night sky. The contrast between this long-period, potentially pristine comet and the more familiar, predictable Atlas or Lemmon discoveries highlights the diversity of objects that traverse our solar system, making each observation a lesson in both astronomy and cosmic history. Moreover, studying this comet provides a rare chance to compare different classes of comets within the same temporal window. Observations of its activity, brightness, and tail formation can be contrasted with those of the 2025 arrivals, which may have experienced previous solar encounters or originate from closer regions of the solar system. Such comparative studies are essential for understanding the influence of origin, composition, and orbital history on cometary behavior. Scientists can investigate questions such as: do long-period comets outburst more dramatically than recently perturbed objects? How does solar heating affect a largely pristine nucleus compared to one that has already made several perihelion passages? The answers help refine models of comet formation, evolution, and the delivery of volatile materials to the inner solar system. The discovery of this comet also underscores the collaborative nature of modern astronomy. Observatories worldwide will monitor it across multiple wavelengths, capturing data on gas emissions, dust production, and tail morphology. Spectroscopic observations may reveal water, carbon monoxide, and organic molecules, offering a chemical fingerprint that can be compared with other comets from different regions of the solar system. By integrating these observations, astronomers can better understand the diversity of cometary compositions, trace the origins of various comet families, and reconstruct the early solar system's chemical environment. This comet reminds us of the enduring value of the Oort Cloud as a repository of ancient solar system material. Each time a comet like this ventures inward, it carries with it information from a region of space that has remained largely untouched for billions of years. Observing this comet alongside Swan, Lemmon, the Atlas discoveries, and the Newcomer from maps creates a rare opportunity to witness the interplay of both familiar and distant cosmic travelers, each contributing to a broader understanding of the solar system's dynamic nature. As it approaches perihelion in January 2026, this comet will not only add to the spectacle of the comet season, but also deepen our appreciation for the vast icy frontier at the edge of our solar neighborhood. The story of C 2024 E1 Vosh naturally leads us to the larger context of the Oort Cloud, the vast distant reservoir from which comets like this originate. The Oort Cloud is thought to extend from roughly 2,000 astronomical units to nearly 100,000 AU from the Sun, forming a spherical shell of icy bodies that have remained largely undisturbed since the solar system's formation. Comets that emerge from this remote region are essentially time capsules, preserving the primordial materials that coalesced to form the planets, moons, and other solar system bodies billions of years ago. When one of these deep time messengers begins its long journey toward the Sun, astronomers gain an unprecedented window into the early solar system, allowing a rare glimpse at the original composition and structure of these primordial objects. These Oort Cloud comets, including Vosh, are typically long-period visitors, with orbits that can span tens or even hundreds of thousands of years. Unlike the periodic comets that return predictably, they are usually one-time travelers, having been nudged inward by gravitational interactions, sometimes by passing stars, other times by galactic tides. Their sudden appearance in the inner solar system is a stark reminder of the dynamic processes at work in the farthest reaches of our planetary system. Each comet that arrives from this distant frontier carries with it chemical signatures and isotopic ratios that reflect the conditions of the solar nebula at the time of planetary formation, providing researchers with clues about the origins of water, organic molecules, and other volatile compounds on Earth and elsewhere. Observing Oort Cloud comets is both a challenge and an opportunity. Because they have been largely untouched by repeated solar heating, their surfaces are often coated with pristine ices, which can produce spectacular outgassing when exposed to the Sun's radiation for the first time. These outgassing events create the characteristic comae and tails that make comets visible from Earth, but they also provide a chemical laboratory for astronomers to study. Instruments ranging from optical telescopes to infrared sensors and radio antennas can detect the composition of gases and dust released from the nucleus, revealing molecules such as water vapor, carbon monoxide, carbon dioxide, and complex organics. Such data allow scientists to compare newly arrived Oort Cloud comets with those from the Kuiper Belt, or short-period periodic comets, helping to piece together the chemical diversity and evolutionary history of the solar system. The Oort Cloud also emphasizes the vast scale of our solar system and the fragility of these icy wanderers. Perturbations from passing stars or galactic gravitational forces are often enough to dislodge these bodies from their distant, stable orbits, sending them on long journeys toward the Sun. Because of this, each comet from the Oort Cloud is a rare and precious opportunity. Once it passes perihelion, it may continue outward into interstellar space, never to return. In this sense, Vosh and its companions are not merely objects of observation. They are messengers from the edge of the solar system, carrying within them records of a time when our planetary neighborhood was forming before the Earth even existed. The arrival of Oort Cloud comets in the same season as more familiar objects like Swan, Lemmon, and the Atlas discoveries adds depth to our understanding of the solar system's dynamics. By studying both newly arrived long-period comets and short-period periodic comets, astronomers can examine contrasts in composition, activity, and response to solar heating. While short-period comets may have been seasoned by repeated perihelion passages, Oort Cloud visitors offer a snapshot of pristine conditions. This contrast enriches scientific inquiry, providing a natural laboratory for testing theories about the evolution of icy bodies, the distribution of volatile compounds, and the processes that govern cometary outbursts. Furthermore, Oort Cloud comets like Vosh serve as reminders of the interconnectedness of the solar system. They are influenced by the distant gravity of the Sun, nearby stars, and even the tidal effects of the Milky Way galaxy, linking the solar system to the broader dynamics of the galactic environment. Their journeys underscore that the solar system is not an isolated system, but a component of a larger cosmic ecosystem, where even objects at the farthest edges can be perturbed into paths that eventually bring them into view from Earth. Observing these comets allows astronomers to study not only the objects themselves, but also the gravitational interactions that guide their movements over millennia. The Oort Cloud connection highlights the philosophical and human significance of observing such comets. Each one is a visitor from a distant past, carrying with it stories of solar system formation and the processes that created the building blocks of planets and life. In the context of the 2025 to 2026 Comet season, the presence of Vosh among Swan, Lemmon, Atlas, and MAPS comets reminds us that the sky is alive with travelers from both near and far, from interstellar space and the distant reaches of our own solar system. Each observation is a chance to witness the movement of these cosmic time capsules, bridging the present with a formative epoch billions of years ago. As the cosmic procession continues, the focus shifts from the rare, long-period visitors of the Oort Cloud to a more familiar traveler, 24P Schaumasse. Unlike the newly discovered comets of 2025 or the deep-time messenger Vosh, this comet is a periodic visitor, returning to the inner solar system on a predictable orbit. First observed in 1911, Schaumasse belongs to the family of short-period comets, which typically orbit the Sun in less than 200 years, allowing astronomers to anticipate their return and study their behavior over multiple passages. Its upcoming perihelion in early 2026 provides a reliable opportunity for observation, contrasting sharply with the one-time appearances of many Oort Cloud and interstellar comets. The predictability of 24P Schaumasse stems from its well-established orbital parameters. Its path around the Sun is relatively stable, influenced only modestly by gravitational interactions with planets, particularly Jupiter. Because astronomers have been tracking Schaumasse for over a century, its orbit can be calculated with high precision, allowing skywatchers and researchers alike to determine when and where it will appear. This predictability is invaluable for long-term studies, as repeated observations reveal how the comet's nucleus evolves with each perihelion passage, including changes in activity levels, outgassing rates, and tail morphology. Schaumasse's periodic nature also allows for comparative studies across multiple returns. Astronomers can examine how repeated solar heating alters the comet's surface, potentially depleting volatile ices, reshaping the nucleus, or affecting the dust-to-gas ratio in the coma. This creates a stark contrast with one-time visitors like Vosh, which carry nearly pristine ices from the outer solar system. By observing both periodic and non-periodic comets within the same season, scientists gain a broader understanding of how solar exposure, orbital history, and composition influence cometary behavior. Schaumasse, with its established track record, serves as a benchmark for evaluating the evolution of other comets in the 2025 to 2026 cosmic lineup. For observers on Earth, the return of Schaumasse offers a reliable target for telescopic study. While its brightness may not rival that of dramatic newcomers like Swan or Lemmon, its predictability allows both professional and amateur astronomers to prepare observation schedules, track changes over time, and conduct detailed imaging and photometry. In many ways, Schaumasse functions as a reference point, amidst a season of more unpredictable comets, providing consistent data against which the behavior of newly discovered objects can be compared. This consistency is particularly valuable when multiple comets are visible over the same months, as it anchors scientific analysis and public engagement in a familiar, trackable object. The recurring appearance of Schaumasse also underscores the importance of long-term monitoring in cometary science. By tracking its orbit and activity over decades, astronomers can detect subtle perturbations caused by planetary encounters, changes in the comet's rotational period, or signs of fragmentation. Such longitudinal studies reveal not only the evolution of a single comet, but also the broader processes that govern short-period comet populations. They help refine predictive models for other periodic comets and contribute to our understanding of the solar system's dynamical stability over time. Furthermore, Schaumasse's return highlights the diversity of cometary experiences within a single season. While interstellar and Oort Cloud comets like 3I Atlas and Vosh provide glimpses into the distant past and the farthest reaches of our solar system, periodic comets such as Schaumasse illustrate the more regular, cyclical rhythms of our cosmic neighborhood. Together, they create a rich tableau for observation and study, showing both the rare and the familiar, the unpredictable and the dependable, within the same sky. Ultimately, 24P Schaumasse exemplifies how predictable periodic comets serve as anchors in the broader cometary landscape. Its scheduled return in early 2026 ensures a steady opportunity for observation, scientific analysis, and public engagement, complementing the excitement and unpredictability of the newly discovered comets of 2025. By including both long-period, one-time visitors and recurring periodic comets in the same cosmic narrative, astronomers can build a more complete understanding of the solar system's icy population, their behaviors, and their contributions to the evolving story of our dynamic night sky. The ongoing observation of 2025 to 2026 comets provides an ideal opportunity to explore one of the most fundamental distinctions in cometary science: the difference between periodic and non-periodic comets. This comparison not only clarifies the behaviors and origins of these icy bodies, but also illuminates the larger dynamics of the solar system itself. Periodic comets, like 24P Schaumasse, are characterized by their relatively short, predictable orbits. They typically complete a revolution around the Sun within a few decades or centuries and return to the inner solar system on a regular schedule. Non-periodic comets, in contrast, are generally long-period visitors or even interstellar objects, such as 3I Atlas, Swan, or C20, 24 E1, Vosh, whose orbits span thousands to millions of years, or in the case of interstellar comets, originate entirely outside our solar system. These distinctions have profound implications for both the study and observation of comets, influencing everything from observational strategies to our understanding of the solar system's formation history. Periodic comets occupy a predictable and relatively well understood niche. Their orbits, often influenced by the gravity of planets, most notably Jupiter, allow astronomers to forecast their returns with remarkable accuracy. This predictability provides the scientific community with the luxury of planning extended observation campaigns well in advance. By contrast, non-periodic comets often appear unexpectedly, with little time between discovery and perihelion, presenting observational challenges and uncertainties. The arrival of a non-periodic comet is often treated as a rare event, particularly for those originating from the distant Oort Cloud or interstellar space, which may only pass through the inner solar system once. Observing these objects becomes a race against time, where astronomers must act quickly to gather as much data as possible before the comet retreats into the darkness of space, possibly forever. The behavioral differences between these two classes of comets are equally striking. Periodic comets, having passed near the Sun on multiple occasions, tend to have surfaces that are relatively depleted in volatile materials. This repeated solar heating can erode the outer layers of ice, leaving a more crusted or dust-covered nucleus. Their activity, manifested through the production of gas and dust forming comae and tails, is often more subdued or predictable, with fewer dramatic outbursts than might be seen in one-time visitors. Non-periodic comets, on the other hand, are often pristine, having never before encountered the intense heat of the inner solar system. When they approach the Sun, the sudden sublimation of previously frozen volatiles can produce unpredictable, sometimes spectacular flares, causing rapid brightening and the formation of extensive tails. Swan's sudden outbursts and unexpected visibility earlier in 2025 exemplify this dynamic behavior, showcasing how non-periodic comets can dominate attention with their dramatic ephemeral displays. From an orbital perspective, the differences are profound as well. Short-period comets generally reside within the gravitational influence of the major planets, often originating from the Kuiper belt or scattered disk. Their orbits tend to be confined, allowing for repeated perihelion passages at predictable intervals. Long-period and non-periodic comets, in contrast, usually originate from the distant Oort Cloud or beyond, where their trajectories are influenced by a combination of galactic tides, passing stars, and minor perturbations over millions of years. This means that their entry into the inner solar system is often the result of random gravitational nudges rather than cyclical orbital patterns. The rarity and unpredictability of these arrivals highlight the dynamic nature of the solar system's outer regions and underscore how celestial mechanics can send ancient frozen bodies plunging toward the Sun after millennia of dormancy. In addition to differences in orbit and activity, periodic and non-periodic comets serve complementary roles in scientific research. Periodic comets allow for longitudinal studies, where repeated observations over multiple returns provide a record of how a nucleus evolves, how dust and gas emissions change over time, and how interactions with planets influence their orbits. Non-periodic comets, in contrast, offer snapshots of conditions that have remained largely unchanged for billions of years. These pristine visitors can reveal the original chemical compositions of the solar nebula, offering insights into the materials present during the formation of the Sun and planets. By studying both types in parallel, astronomers can construct a more complete narrative of solar system evolution, spanning the early, unaltered conditions preserved in distant icy bodies and the transformative effects of repeated solar exposure on more familiar, short-period comets. The visual and observational experiences provided by these two classes of comets also differ. Periodic comets tend to be more predictable in both brightness and location, making them reliable targets for amateur astronomers, educational outreach, and long-term monitoring projects. Observing Schaumasse as it returns in early 2026, for instance, allows observers to track subtle changes in brightness and tail morphology, comparing these data to previous returns to detect evolutionary patterns. Non-periodic comets, however, often create a sense of urgency and wonder precisely because of their unpredictability. When a new Oort Cloud visitor or interstellar comet is discovered, observers have limited time to capture the fleeting spectacle before it recedes back into the void. This unpredictability fosters excitement, rapid mobilization of observational resources, and international collaboration to capture as much data as possible. Another important aspect is the chemical diversity revealed by these two groups. Periodic comets may have lost more of their most volatile ices due to repeated perihelion passages, leaving a predominance of less volatile compounds. Non-periodic comets, particularly those arriving for the first time, often release a richer and more varied array of gases as solar heating triggers sublimation of pristine ices. Studying these emissions allows scientists to compare isotopic ratios, molecular abundances, and dust-to-gas compositions, offering clues about both the origin of the comets and the early solar system environment. The interplay between these findings from periodic and non-periodic comets has been crucial in refining models of solar system formation and understanding the distribution of water and organic molecules across different reservoirs of icy bodies. The timing of cometary appearances also emphasizes the unique dynamics of 2025 to 2026. With multiple non-periodic comets entering the inner solar system in close succession, Swan, Lemmon, Atlas discoveries, and Vosh, combined with the predictable return of Schaumasse, observers are presented with a rare juxtaposition of the predictable and the ephemeral. This convergence allows for comparative studies under similar solar conditions, providing a natural laboratory to investigate how varying origins, orbital histories, and prior solar exposure influence activity, brightness, and tail development. Observing these comets collectively enhances understanding of solar system dynamics, highlighting the interplay between gravitational mechanics, solar radiation, and the physical properties of icy bodies. The 2025 to 2026 period has emerged as an unusually active window for comet observation, a phenomenon that has caught the attention of both professional astronomers and amateur skywatchers alike. While comets appear throughout the year, and every year brings some level of activity, the sheer number of new arrivals during this particular 2-year span is remarkable. One reason for this apparent boom is a combination of gravitational influences that have nudged multiple long-period comets from the Oort Cloud and scattered disk toward the inner solar system simultaneously. Such alignments are relatively rare on human timescales, and when they occur, they can produce a cascade of cometary visitors within months of each other, as we are seeing with Swan, Lemmon, the Atlas discoveries, and Vosh. These gravitational perturbations, often subtle over decades or centuries, can destabilize distant icy bodies, sending them on inward trajectories that culminate in visible appearances from Earth. Another contributing factor to the 2025 to 2026 comet boom is the ongoing improvement in detection capabilities. Surveys like Atlas, Lemmon, and MAPS, equipped with high-sensitivity telescopes and automated detection algorithms, have dramatically increased the rate at which faint or fast-moving comets are discovered. Many of the comets that were once too dim to detect until they were very close to the Sun are now being discovered earlier in their journeys, giving observers more time to study them. This technological advance, combined with increased global coordination among observatories, means that comets that might have gone unnoticed in previous decades are now being identified, catalogued, and tracked systematically. As a result, even if the intrinsic number of comets entering the inner solar system were constant, our perception of a boom is heightened by our to detect and monitor them more effectively than ever before. The timing of 2025 to 2026 also coincides with several favorable orbital alignments. The Earth's position relative to the incoming trajectories of these comets ensures that many of them will be observable from both hemispheres, increasing the likelihood of widespread visibility. This is particularly important for bright comets like Swan and Lemmon, whose apparent magnitudes could place them within reach of binoculars, or even the naked eye under dark skies. The orbital dynamics not only affect visibility, but also the rate at which these comets accelerate toward perihelion, influencing their apparent speed and brightness from an Earth-based perspective. When multiple comets arrive under such favorable conditions, it creates a concentrated period of celestial activity that is highly unusual, offering observers the rare experience of tracking several comets within a short time frame. Beyond gravitational nudges and observational technology, there may also be stochastic factors contributing to the perceived surge in comets. Cometary orbits are affected by myriad influences over long periods, including interactions with giant planets, non-gravitational forces caused by asymmetric outgassing, and even collisions with smaller solar system bodies. These small but cumulative effects can occasionally align to produce a cluster of inbound comets over a short interval. While each comet's journey is unique, the simultaneous arrival of multiple objects in 2025 to 2026 appears to be the result of such a rare convergence of forces, producing a natural wave of cometary visitors that enhances both scientific opportunities and public interest. From a scientific standpoint, this concentrated influx of comets offers unprecedented comparative opportunities. Observing multiple objects with different origins, orbital histories, and physical compositions allows astronomers to study how these factors influence cometary behavior. For example, comparing Swan, which may produce unpredictable outbursts, with the more predictable periodic 24P Schaumasse, can reveal how prior solar exposure affects activity levels, gas emissions, and dust production. Similarly, studying Vosh alongside the Atlas discoveries highlights differences between Oort Cloud comets and objects perturbed from closer regions of the solar system. This convergence of observational targets within a narrow window of time effectively transforms the 2025 to 2026 period into a natural laboratory for understanding the diverse population of icy bodies that traverse our solar system. The comet boom also has implications for public engagement and outreach. In previous decades, comet appearances were often sparse, with years passing without any bright or easily visible comets. The clustering of multiple comets in 2025 to 2026 provides not only scientists, but also amateur astronomers, educators, and astronomy enthusiasts with repeated opportunities to experience these cosmic visitors firsthand. Bright comets visible with modest equipment or even the naked eye generate excitement, inspire interest in astronomy, and create opportunities for citizen science projects, such as monitoring brightness changes, photographing tails, or recording positional data. In this sense, the current comet surge enhances the cultural and educational impact of these objects, fostering a broader appreciation for the dynamic nature of our solar system. Meteor showers, which often accompany cometary debris, may also be indirectly affected by this boom. As comets approach perihelion and shed material, Earth may intersect these trails, producing meteor events. While not every comet contributes directly to observable meteor activity, the overall increase in cometary presence raises the potential for such events, providing another avenue for engagement and scientific study. This connection between incoming comets and meteor phenomena further underscores the broader influence that these icy travelers have on our near-Earth environment and highlights the interconnectedness of solar system processes. The 2025 to 2026 comet boom is a vivid reminder of the dynamic and ever-changing nature of the solar system. While the Sun, planets, and familiar night sky objects appear stable on human timescales, the arrival of multiple comets within a relatively short interval showcases the underlying dynamism of our celestial neighborhood. Each comet, whether an interstellar visitor like 3I Atlas, a new discovery like the Atlas or MAPS comets, a long-period Oort Cloud visitor like Vosh, or a predictable periodic comet like Schaumasse, adds a layer of complexity, surprise, and opportunity for observation. Collectively, they create a season unlike any in recent memory, one that not only captivates observers, but also advances scientific understanding by providing a rich, temporally concentrated sample of the solar system's icy population. In short, the convergence of gravitational alignments, enhanced detection technologies, favorable orbital geometries, and the rare alignment of multiple cometary pathways has produced an extraordinary surge of comets for the 2025 to 2026 observing window. For astronomers, it is a rare chance to conduct comparative studies and gather extensive data sets. For the public, it is a spectacular opportunity to witness the beauty and unpredictability of these cosmic wanderers. The comet boom is both a scientific gift and an invitation to reconnect with the night sky, reminding us that, even in an era of advanced space telescopes and automated surveys, the solar system continues to surprise and inspire. As we continue to follow this extraordinary procession of comets in 2025 to 2026, one of the most compelling questions for both professional astronomers and casual skywatchers is just how bright these celestial visitors might become. Predicting a comet's brightness is notoriously tricky, as it depends on a delicate interplay of factors, including its size, composition, proximity to the Sun, and the behavior of its volatile ices. Some comets, like Swan, have already exhibited rapid brightening and potential for spectacular outbursts, raising the tantalizing possibility of naked eye visibility in mid-October 2025. Others, such as the Atlas discoveries and MAP's Newcomer, may remain faint objects, detectable only with the aid of telescopes or binoculars. This variability underscores the inherent unpredictability of cometary activity and makes every new observation a potential surprise. Brightness is primarily influenced by a comet's outgassing activity as it approaches the Sun. When solar radiation warms the nucleus, ices sublimate into gas, releasing dust particles that form the visible coma and tail. Larger nuclei with abundant volatile materials tend to produce more impressive displays, while smaller or depleted comets may only develop modest coma that remain invisible to the unaided eye. Comets from the Oort Cloud or interstellar space, like Vosh or 3I Atlas, often carry pristine ices that can lead to dramatic flares, sometimes increasing in brightness over short periods in unexpected ways. Periodic comets, by contrast, may have surfaces depleted by previous perihelion passages, producing steadier but generally less spectacular light curves. Historical data and modelling provide some guidance but cannot guarantee precise predictions. For example, Swan has already shown signs of unpredictable outbursts, demonstrating that a comet can sometimes exceed expectations dramatically. Astronomers use brightness parameters such as absolute magnitude and the rate of brightening per astronomical unit of approach to the Sun to estimate visibility. But these calculations can be upended by sudden jets or fragmentation events. Similarly, Lemmon and the Atlas comets have well-characterized nuclei sizes and predicted trajectories, but the exact levels of activity remain uncertain until closer observation. Even a faint telescope target can surprise observers with sudden flares or changes in tail structure, emphasizing the excitement of real-time comet monitoring. The viewing experience for each comet will also vary based on location, time, and sky conditions. Comets reaching perihelion during moonless nights or appearing high in the sky from populated observing regions offer the best opportunities for casual observers. Conversely, comets approaching perihelion in daylight hours or low on the horizon may remain challenging, even if intrinsically bright. Observers are encouraged to track predictions of magnitude, elongation, and optimal viewing windows to maximize their chance of witnessing these icy visitors. Amateur astronomers equipped with small telescopes or binoculars may still capture stunning views of comae and tails for comets that are too faint for the naked eye, while long-exposure astrophotography can reveal intricate tail structures and jets invisible to casual observers. Some comets may also surprise with the evolution of their tails. Dust and gas tails react differently to solar radiation and solar wind, producing dynamic shapes that can vary on timescales of hours or days. For example, Swan's unpredictable outbursts could generate tails that suddenly lengthen or develop multiple streams, offering dramatic visual phenomena for observers. Periodic comets like Schaumasse, while generally more stable, can also display subtle variations, such as changes in tail length or brightness at certain points in their orbits. Monitoring these variations provides important scientific data on dust grain sizes, gas composition, and the effects of solar radiation pressure. The potential brightness of these comets is not merely an aesthetic concern, it has scientific implications as well. Brighter comets allow for more detailed spectroscopic analysis, enabling the detection of volatile compounds, isotopic ratios, and organic molecules. These observations can illuminate the primordial chemistry of the solar system, reveal differences between comet populations, and refine models of comet formation and evolution. Even relatively faint comets, when studied systematically, contribute valuable insights into activity levels, rotational periods, and the physical properties of nuclei. The brightness, therefore, directly influences the quality and quantity of scientific data that can be obtained. In the 2025 to 2026 comet season, the combination of potential naked-eye comets like Swan, binocular targets like Lemmon, and fainter telescope objects like the Atlas and MAPS discoveries creates a diverse observational landscape. This variety ensures that observers of all levels, from casual enthusiasts to seasoned professionals, have opportunities to engage with these icy visitors. The season exemplifies the full spectrum of cometary experiences, from dramatic, sudden appearances that command attention to subtle, gradual increases in brightness that reward patient monitoring. Each comet contributes its own chapter to the story of this celestial parade, adding layers of complexity, excitement, and scientific value. Ultimately, setting expectations for brightness emphasizes the dual nature of comets. They are both objects of wonder and laboratories of discovery. Some may flare into view and inspire awe, while others remain faint but scientifically invaluable. This variability is part of what makes cometary observations so captivating. As Swan, Lemmon, the Atlas and MAPS comets, Vosh and Schaumasse journey across the sky in the next year or so, observers can look forward to a season of surprises, revelations, and the simple joy of witnessing cosmic travelers from across the solar system and beyond. The simultaneous arrival of multiple comets in 2025 to 2026 presents a unique scientific opportunity, allowing astronomers to study a cluster of cometary visitors in succession and gain insights that would be impossible from isolated observations. When several comets, such as Swan, Lemmon, the Atlas discoveries, MAPS, Vosh, and periodic Schaumasse, appear in the inner solar system within a short time frame, researchers can conduct comparative analyses that reveal subtle differences and surprising similarities in composition, activity, and behavior. By observing these icy bodies collectively, scientists can examine how their origins, interstellar, Oort Cloud, Kuiper belt, or short-period periodic, affect their physical properties and interactions with the sun's radiation and solar wind. Such sequential observations act as a natural laboratory, where the variations among comets illuminate the diversity of the solar system's small body population. One key area of study is the chemical composition of cometary nuclei. Each comet releases gas and dust as it approaches the sun, and the specific molecules detected, water, carbon monoxide, carbon dioxide, ammonia, methane, and complex organics, can provide clues to the environment in which the comet formed. When astronomers track a series of comets in a single season, they can compare the relative abundances of these compounds across objects with different origins and orbital histories. For example, long-period Oort Cloud comets like Vosh may reveal a richer or more pristine chemical signature, than short-period comets like Schaumasse, which have been exposed to repeated solar heating over centuries. These comparisons help scientists reconstruct the primordial conditions of the solar nebula and understand how the distribution of volatiles varies across the solar system. Studying a cluster of comets also provides valuable information about the dynamics of cometary activity. By monitoring how comets develop comae and tails as they approach perihelion, astronomers can identify patterns in outgassing, the formation of jets, and fragmentation events. Comets like Swan, known for unpredictable flares, highlight the extremes of activity, whereas periodic comets provide a baseline of expected behavior. Observing multiple comets in close temporal proximity allows researchers to investigate whether environmental factors, such as solar activity or the heliocentric distance of approach, influence activity levels. This approach also offers insights into rotational dynamics, as rotational periods and axial tilts can affect the rate and direction of gas and dust ejection. Another scientific benefit is the study of dust production and tail morphology. By following multiple comets, astronomers can analyze the interplay between dust grain sizes, radiation pressure, and the solar wind. Differences in tail structure, whether straight, curved, bifurcated, or multiple stream, can indicate variations in particle composition and ejection mechanisms. Observing these features across a series of comets allows for statistical analyses, helping to refine models of tail formation and the physical processes that govern cometary evolution. High-resolution imaging, spectroscopy, and long-term monitoring all contribute to a deeper understanding of how cometary material behaves once released into space. The presence of multiple comets in a single season also enables coordinated international campaigns. Astronomers from around the world can synchronize observations to cover different wavelengths, time zones, and instrumental capabilities, creating comprehensive datasets that capture transient phenomena like outbursts or fragmentation. Such coordinated efforts are particularly valuable when dealing with rare long-period comets or interstellar visitors, where a single missed opportunity could result in lost data. By observing a sequence of comets over weeks or months, researchers can apply lessons learned from earlier targets to optimize the observation of subsequent arrivals, improving both efficiency and scientific output. Monitoring a cluster of comets also provides practical insights into orbital mechanics and gravitational interactions. As each comet travels through the inner solar system, its trajectory is influenced by the Sun, planets, and other gravitational sources. By comparing the paths of multiple comets, astronomers can test models of how perturbations affect long-period and short-period orbits, refine predictions for future returns, and understand the mechanisms that bring distant objects into the inner solar system. In the case of interstellar visitors like 3I Atlas, following a series of comets allows scientists to compare hyperbolic or near-hyperbolic trajectories with the more elliptical paths of Oort Cloud and periodic comets, deepening our understanding of both solar system and interstellar dynamics. Another dimension of scientific value comes from studying cometary evolution over short timescales. With multiple comets observable in the same period, researchers can examine how quickly nuclei develop visible comae, how tail structures change, and how brightness evolves in response to solar heating. This provides a comparative framework for assessing the influence of nucleus size, volatile content, and orbital history on observable phenomena. By building a dataset across several comets, astronomers can distinguish between behaviors that are intrinsic to a comet and those that result from environmental effects, such as proximity to the Sun or interactions with the solar wind. As the comets of 2025 to 2026 continue their journeys through the inner solar system, it is impossible not to step back and marvel at the cosmic choreography unfolding above us. This celestial parade, comprising interstellar travelers like 3I Atlas, unpredictable newcomers such as Swan and Maps, Distant Oort Cloud visitors like Vosh, well-established atlas discoveries, and predictable periodic comets like Schaumasse offers a rare, almost theatrical spectacle of nature in motion. Each icy wanderer carries with it a story, a frozen archive of the solar system's history, or even material from beyond, crossing vast stretches of space to briefly illuminate our skies. Together, they remind us that the universe is not static, but vibrant and dynamic, a place where change is constant and the unexpected is always possible. The interplay between the predictable and the unpredictable adds layers of fascination. Periodic comets, returning on their established schedules, demonstrate the solar system's enduring order and the persistence of orbital mechanics over centuries. They offer stability, reference points, and repeated opportunities for study, anchoring our understanding of cometary behavior. In stark contrast, interstellar and Oort Cloud comets arrive as fleeting, mysterious visitors, unpredictable in their brightness, paths, and activity. Their sudden appearances inject excitement, surprise, and a sense of wonder, highlighting that even in a system governed by physics, there is room for the extraordinary. Observing these contrasting visitors in the same season magnifies the beauty and diversity of the cosmic stage. Beyond the visual spectacle, each comet in this parade serves as a messenger from the distant past. Their nuclei, often containing ices and dust untouched for billions of years, preserve the chemical signatures of the early solar system, or in the case of interstellar comets, regions far beyond it. By studying them, astronomers unlock secrets of planetary formation, the distribution of water and organics, and the processes that sculpt small bodies in space. The scientific value of observing a sequence of comets cannot be overstated. It is an unprecedented opportunity to compare origins, compositions, and behaviors under similar solar conditions, effectively using the 2025 to 2026 season as a live laboratory of cosmic evolution. The visual and emotional impact of this parade also resonates with the human imagination. For centuries, comets have been symbols of both awe and forewarning. Today, our understanding has grown, and yet the thrill of witnessing a comet flare in the sky remains profoundly moving. Observers can track Swan's unexpected brightening, watch Lemmon gracefully sweep across the sky, or anticipate the arrival of Schaumasse with its familiar cadence, all while reflecting on the immense distances these objects have traveled to reach us. The juxtaposition of the ancient and the contemporary, the one-time visitor and the returning traveler, creates a narrative that connects humanity with the wider cosmos. There is also a subtle lesson in the diversity of these icy wanderers. Interstellar comets remind us that the solar system is not isolated. It is part of a galactic environment where material from other stars can traverse interstellar space and briefly enter our celestial neighborhood. Oort Cloud comets, on the other hand, represent the outermost reaches of our own system, a vast repository of primordial objects shaped by billions of years of gravitational influences. Periodic comets provide continuity, demonstrating how even small bodies are subject to predictable cycles and evolutionary processes. Together, they paint a picture of the solar system as a living, breathing entity, a dynamic environment where celestial objects move, interact, and evolve. For astronomers, this parade is both a scientific boon and a reminder of the interconnectedness of celestial mechanics, chemistry, and observational strategy. The simultaneous observation of multiple comets in 2025 to 2026 allows for comparative studies that deepen our understanding of formation processes, orbital dynamics, and the long-term evolution of small bodies. Each observation, whether capturing a sudden flare, a dust jet, or subtle compositional detail, contributes to a broader mosaic of knowledge about our cosmic environment. It is a reminder that even with advanced telescopes and decades of study, the solar system continues to surprise, offering new data and fresh insights at every turn. For the public, these comets provide a rare opportunity to witness the solar system in motion. From backyard telescopes to wide-field astrophotography, each comet offers a chance to connect with the universe directly. They inspire curiosity, wonder, and a sense of participation in the ongoing story of space exploration. Watching Swan, Lemmon, Atlas, MAPS, Vosh, and Schaumasse in succession allows observers to perceive the solar system not as a static backdrop, but as a dynamic, living sky, full of movement, light, and frozen travelers that bridge the gap between the ancient past and the present moment. Ultimately, the 2025 to 2026 Comet Parade reminds us that our solar system is far from inert. It is a place of motion, transformation, and occasional surprises, where icy messengers from distant reaches, both interstellar and native to our own Oort Cloud, arrive to offer glimpses into the past, opportunities for discovery, and moments of wonder. Each comet is a fleeting spectacle, yet together they form a seasonal narrative that enriches our understanding and appreciation of the cosmos. Observing them encourages reflection on our place in the universe and the extraordinary dynamism of the celestial environment that surrounds our small blue planet. In this parade of icy wanderers, we see not only the marvel of individual comets, but the larger story of a solar system alive with motion, history, and possibility. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.